Welcome to Triple Integrals and your Calculus 3. It's exciting stuff, triple integrals. I know. You did double. Get ready for triple. Yeah, are you going to see like 3 integral symbols in a row? Absolutely, you're going to see 3 in a row. That's the joy and beauty of triple integrals. Yeah, good stuff. So let's do a quick derivation of it so you can see what the heck you even would use it for. And we're going to use it for a couple things. We're going to use it to find the volume of a solid. Hey, wait a minute. I thought you said you could use a double integral to find the volume of a solid. I did, but you can also use a triple integral if you prefer. So now you're going to learn 2 ways to find the volume of a solid. Cool. And you can use it to find the mass of a solid. And there's more, but we're not going to learn that here. That'll come later. So let's do the derivation of a triple integral. All right, fine. Let's say you had a function of 3 variables, f, x, y, z, which you cannot graph. Okay, cannot graph it. Well, what's that diagram to the right? That diagram is not a graph of f, x, y, z. That is going to be the graph of a region, a solid region, that we're going to integrate this f, x, y, z over. In other words, we're going to go triple, 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 and this f, x, y, z will go in the integrand, but we're not graphing him. Okay, we're not graphing him. The solid region that we're going to call Q. Some textbooks call it E. I think your textbook likes to call it big D. Whatever. It depends on the textbook what they're going to call the solid. Okay, E, D, Q, whatever. Name it. We already used up R. R is used up because we're going to use R for a region in the XY plane that's 2-dimensional. But now we're going to integrate over a 3-dimensional thing. And this is the 3-dimensional thing. We're going to encompass this solid Q with a bunch of boxes, like a cage of boxes that lie entirely within Q. And then we're going to consider a random little teeny tiny ith box. We're going to find his volume. So the volume of an ith box, call it delta V sub I, would be the length times the width times the height of said little box. And that'll just be some delta x sub I times delta y sub I times delta z sub I. Fine. The norm of our partition, which kind of looks like you're doing a magnitude, and that's denoting the length of the longest diagonal of the n boxes that you see in a partition. Yep. Choose a point in each box, form a Riemann sum. Yeah, you're going to do a sigma. And you're going to sum the product of this function with all the volumes. Now, this function, well, what could the function be? Well, it could represent different stuff. But one of the things that's typical is it could be a density function for that solid. Okay. And then, real quick, we're going to take the limit as the norm of the partition goes to 0, and the Riemann sum is going to turn into an integral, specifically a triple integral. Yeah. So if f is continuous over your solid Q, then the triple integral of, I did not ask for that. Sorry. Nope. Is the triple integral of f over Q, and you're going to have a dV here. dV stands for the volume element, and that's equal to the limit as the norm of the partition goes to 0. Sigma I going from 1 to n, f evaluated at x sub I, y sub I, z sub I, delta v sub I. So this delta v sub I, that turns into dV, as you can see. Now, what about this dV? Provided the limit exists, because it might not. We hope it does. The dV, the volume element, is basically this delta x sub I, delta y sub I, delta z sub I, which could turn into dx, dy, dz. Yeah, but there's 6 possible orders of integration. So I'm just going to rearrange dx, dy, dz in all the possible combinations. So another order could be dy, dx, dz. Or how about dz, dx, dy? Or dx, dz, dy, and dy, dz, dx, and last but not least, dz, dy dx. Well, my gosh, that's a lot of choices. Can you direct us, like, which choice is the best? Or do we have to know everything? Yeah. Well, I don't worry about it. I'll tell you my personal favorite. Right there. I like the dz to be the innermost integral and the dy dx to be the outer ones. My second favorite is this one here, dz dx dy. I don't have a third or a fourth favorite. I don't like any of the other choices. I try to stay away from it if possible. I'm just saying. So what can you use a triple integral for? For now, there's more choices later. And we have to do this evaluation. Man, this whole thing got messed up, huh? Go back to my Word document. I guess it got messed up there too. So do you guys see that in your course reader, or is that hidden also?
We can see it.
You can see it. It's normal for you, but it's bad for me. Okay. Oh, that's a bummer. Okay, so what it should say is you got your theorem, and how do you evaluate one of these triple integrals? Like, what the heck? So you have to iterate them. And so hopefully you have your solid region Q all figured out for what the limits are. So X is going to go hopefully from a pure number to a pure number. So this is how you're going to turn your triple integral into something you can do business with. Boom, boom, boom. You're still going to have that integrand. And then I'm going to do my personal favorite choice. So your outermost integral still has to have pure numbers for limits. So that's not going to change. That rule is still in effect. Your middle integral is allowed to have variables, but the variables it could have can only be the outermost variable of integration. So let's say h1 of x, because they're telling us y goes between the low of h1 of x to a high of h2 of x. And then the innermost integral is allowed to have not itself, not z's, because we're integrating with respect to z, but it could have x's and y's, and so it'll be some function g of xy for the lower limit and g2 of xy for the upper limit. And then hopefully this is integral. And as before, you work your way from the inside to the outside. So if you were given a triple integral, start by trying to integrate the innermost integral first, and then you work your way out until you're to the last outermost shell. Okay? Two things you can use a triple integral for at this moment is volume of a solid. Please note that if you are using it for volume, there's a 1 in the integrand. That's how you know that the triple integral could represent a volume, if there's a 1 in the integrand. If there's something else in the integrand, you can think of this as being a density function of some sort, and you're finding the mass of that solid because you're integrating over the solid still, where the density function, sometimes they call that rho of xyz, just so you know, rho. Okay. So let's do some triple integrals then, and then we'll do one that involves a setup. Those are the hard ones, and that's what makes this module a little bit challenging for some students, is because they're so used to not having to set up a problem. They're used to like, hey, just give me an integral that I'll go do. Okay, fine. And then what if they say go set up the integral? And you're like, uh-oh. So you got to know how to do both. So you're going to project the solid onto the coordinate plane of the outer two variables, and then you can determine the limits of integration the same way we use for double integrals. Okay. So your Z is going to have like a capping surface and an underbelly, and that's how you know the who's taller and who's shorter. And then the projection of the solid onto the XY plane, and you'll look at this region R down here, and that'll help to find the limits of X and Y. If you're involved in the setup. Okay, let's do some easy examples to start. Example one of these two choices is not an okay triple integral. And why not? Because they're violating one of the rules of putting limits on the integral symbols. Can you see which one is not good?
B,
Correct. Why not?
because Z is on the middle integral.
Good. This Z is not okay. That's illegal there. Okay, that's bad math. Why is that illegal? Because the innermost integral is integrating with respect to Z. So we shouldn't be seeing any Z's after we get done with that innermost integral. You don't want to like, okay, now I'll do the next integral in line, which is the middle. Oh, wait a minute, where'd this Z come from? Not good. Okay, this one is okay. It's following all the rules and regulations of putting limits on those integral symbols. Okay, now let's do example 2. And I put example 2 in here just sort of to boost our self-esteem here. It's an easy triple integral. I just want to do one so you get sort of the flow of it. Okay. First step, you do the innermost integral. That's how you work it. Inner layer first. And this one is integrating with respect to x. Oh dear. What does that mean? You hold z and y constant. Well, then what about this thing here? That just looks like some constant with respect to x. So you just copy it down. And the antiderivative is just that constant multiple times x, where x is going to go between the limits of 0 and the square root of 1 minus z squared. Okay. And then that's just going to take us to z over y plus 1, square root of 1 minus z squared. Now this y plus 1 you can just think of as a constant multiple because it is when you're doing the next integral, which is integrate with respect to z. You are going to want to use the power rule with u substitution. So go ahead and tell me the u. Go ahead and tell me the du. Notice I do have a z and a dz in the integrand. Perfect. I just need a -2. Fine. That's always easy to come up with. So I'm going to put a -2 in there, provided I multiply the front by its reciprocal, and then that makes it legal. This now looks like 1 over y plus 1. You got square root of u du going on in there, and then you also have the dy. And you know the square root of u, his integral is found by using the power rule on u to the half, which gives you 2/3 u to the 3/2. Fine. Then what? Yeah. So let me pull that 1 over y plus 1 out. So you're really taking this 2/3 1 minus z squared to the 3/2 and evaluating that guy between the limits of 0 and 1. And then we'll finally integrate with respect to y. Okay. Did you guys see that meme that I had in the last one?
The one that said polar bear?
Yeah. Let me just go.
No, we didn't see
quick.
it.
You didn't see it?
No.
Hang on a minute. We've got to pull that up because we need a little bit of humor here, right? It's always good. So where was that guy? We just finished it. I think I skipped seeing the last page. Here you go. I thought this was cute. There's a polar bear, and then you have a Cartesian bear, right? Cartesian XY.
Yeah, that's a pretty dank meme.
So
Right.
different.
Cute.
I wonder what happened to that other bear.
Then I said, let's use polar coordinates. Ah, ha, ha, ha. Oh, very funny. Back to triple integrals. Okay. So here we are. We're still in the middle of figuring this whole mess out. And this 2/3, I'm going to pull it out in front because you can. Yeah. And then what do we have here? We've got 1 minus 1 squared to the 3/2. Ah, that's going to be 0. Cool. Nice. And then what? So we have 0 minus 1 to the 3/2, which is just 0 minus 1, which is just -1. So you can pull that out in front. And right now, what do we have? We have -1, and then these guys, after reducing, we have a -1/3. And now what's the only thing left? We have the last integral. And that looks like the log rule. Log rule. So you're going to use u sub, u is y plus 1, du is just dy. So we don't have to put anything in there. And so we're just going to get ln of absolute value of y plus 1, and you'll evaluate at the limits. So I get ln 2 minus ln of 1, but ln of 1 is 0. Ooh, that's convenient. Final answer, 1/3 ln of 2. Okay, and that's your first look at a triple integral. It's not that hard. I want to do one more example, and then we'll be done. Okay, and we'll finish this next time. But I want to do one that involves a setup. Okay, and this one was similar to what was on your quiz this week, although it may have looked trickier because your quiz had a plane that had fractions in it. It's still a plane equation. And instead of using a double integral that we're going to set up a volume like you did on that quiz, we're going to use a triple integral. But you'll see the way the double integral one looks soon. So keep your eye out for that. So the question is, what's better, setting it up as a double integral for volume or setting it up as a triple integral for the volume? And the answer is, it's about equally the same, as you'll soon find out. Okay? So they want us to set up a triple integral in rectangular coordinates representing the volume of the solid bounded by this plane and the 3 coordinate plane. So it's going to be in the first octet. So I can even draw a picture of it. They didn't ask me to draw a picture of it, but hey, let's do it for fun. And you know how to find the x, y, and z intercepts of this plane. I get 12 for the x-intercept, 12 for the y-intercept, and 4 for the z-intercept. And so the portion of the plane looks like that in the first octet, and that's one of the sides of the solid. The other side of the solids are just the coordinate planes. So this is like a tetrahedron. It's a 4-sided nice solid. Great, go get the volume. Fine. Okay. So one of the things that you're going to need to do, and you had to do this on the quiz, is you have to solve for z first. And so for this one, it ends up being 1/3 times the quantity 12 minus x minus y. Now you can go ahead and distribute the 1/3 if you want. I don't care. Do it or not. It's 6 of these, half a dozen of the other. Okay. I'm not, so whatever. Now, what's going on in the xy plane? If you look at the base of this solid in the xy plane, you want to know what's going on there. And so I notice I've got a 12 here and a 12 here. Well, how would I know that? Because in the xy plane, you would want to see the trace of this plane as it cuts through the xy plane, because it does. So if you set z equals 0 in the plane equation, you will get what's going on. You'll get x plus y equals 12, but that's going to be the trace y equals 12 minus x. And since it's bounded by the coordinate planes, that means it's bounded by the axes. So this is the base of the solid. Now, why do you care? Well, they didn't ask you to draw the base of the solid. You probably should anyways. Otherwise, you're going to screw up the rest of the problem because you won't put the limits on your integral symbol correct. Okay, so now the volume. Triple, triple, triple. There's a 1 in the integrand when you're doing volume. My personal favorite order of integration, remember there's 6 possibilities. I don't want to do all 6. dz, dy, dx. Now what is z doing? What are the limits for z? Well, the lowest that z gets is the xy plane, which has the equation z equals 0. So the lowest limit for the z will be 0. And what's the highest it gets? Well, the highest it gets is this plane, 1/3 parentheses 12 minus x minus y. That's the upper limit. Now, how do you iterate the x and y integrals? You look at what's going on here in the xy plane. And we notice that dy dx is the vertically simple choice. So if I go back to my little man, oh yeah, he's not going away. Oh no, he's still here. I'm going to draw my vertical little man here. Hey. And I'll do the outermost integral first, since that's always pure numbers. Hey, what's x doing on this little triangular region? 0 to 12. Okay. What is y doing? Well, look at the little man. His head is on that diagonal line, y equals 12 minus x. So 12 minus x is the highest that y gets. And the lowest is what the little man's feet are standing on, but that is the x-axis. But that has the equation y equals 0. You're going to put 0 down there. And this is half the battle. Like, I'm going to give you partial credit if you could at least set up the integral representing the volume. Like, yay, success. And now go integrate it. Oh, man. Yeah. Innermost integral first. Well, the antiderivative of 1 with respect to z is just z. And then have z going between his limits. Okay. And then that's going to end up being this. I'm gonna pause right here. Notice what this is. This is the volume of the solid if somebody had asked you to set up the volume using a double integral. Oh, really? Yeah. So now if I gave you a choice, like, hey, set up the volume of this solid, pick your favorite way. I don't care, triple or a double. For a triple, you would have done this. For a double, you would have put the capping surface right there. And those are both going to give us the same answer. But after you set up a triple and you do that first integration, you end up with the double representing volume. Pretty sweet, huh? Now you know something really that's cool. And then now what? Well, integrate this mess with respect to y. I'm going to pull the 1/3 out because it's a fraction. I don't like fractions. And then when I integrate the stuff inside parentheses, I get that. Yeah. I know, that's pretty gross, huh? Then what? Now it's going to get kind of messy because I'm going from 0 to 12 minus x. And now you can't, I don't allow you to use your graphing calculator. If I do allow it, it's only until the very last step. So you still have to go one more step, and then I'll let you hit the graphing calculator. So go ahead and put in your limits. And this is where you substitute for y here. It's going to be kind of gross. I know. I know. And then plugging in the 0, we get a 0. So this whole mess, you can integrate with respect to x. Now you could just FOIL stuff out and add like terms, and then this wouldn't be too hard to do. But you know, at this point, go use your graphing calculator with the FNINT command. If you don't know how to do that, stay after class or come to office hours. I'll be happy to show you. It's really easy peasy on your graphing calculator. And then you should get, I'll just go etc. each. Final answer, 96 cubic units. Woo! And that is using a triple integral for volume. And that concludes today's lecture. So congratulations. Yay.